I'll talk today specifically about partial crystal disorder, which leaves well-recognizable footprints on the diffraction images. And this is only one of many things that we don't want to see on our diffraction images. I'll show one old example in more detail, and then quickly 4 examples from the last year. Before starting with examples, let's look at the results of auto-processing at DLS. If the results from different pipelines are inconsistent, this is an early sign of possible pathology of your crystal. At this point, we might choose a different data sets for structure determination, or examine our data to see what goes on. For such examination, I usually use Dial's image viewer, Dial's reciprocal lattice viewer, and another most useful tool is Dial's RS mapper. It converts diffraction images into 3D maps that can be visualized in CUD. The example from Rafael Sigas is the best example I know for demonstrating the ghost density due to the partial disorder. The ordered domains are formed by molecular layers which with alternating contacts of type 1 and 2. Defects break the regular sequences of the contacts, but they engage contacts identical to those in the ordered domains. As a result, there is a strict constraint on the relative positions of the adjacent domains. Note that this model of defect is not derived from direct observations. This is only a hypothesis that, however, agrees very well with X-ray data. The same applies to all other examples. Right, schematic on the right links us to the next slide, where 3 crystals are compared, one without defects, one with few, and one with many of them. What is the few and what is the many depends on the coherence length of X-rays. Few defects and large order domains are when most X-ray photons see only a part of a single domain. In this case, like in the central scheme, in this case, diffraction pattern cannot be distinguished from the diffraction of the single crystals on the left. Many defects and small domains are when the most X-ray photons see 2 or more ordered domains, as on the right figure. This case referred to as partial crystal disorder. Right, break spots are because of the 3-dimensional translational symmetry of the crystal. Samples with 2-dimensional periodicity will exhibit streaks with variable intensities spanning in the direction of the missing periodicity. We are in the between because we have local translational symmetry inside the ordered domains. Spots are there, but some of them can be seen, yes. Spots are there, but some of them have heavy tails that merge together. The difference between the columns of reflections is because of specific offset between the adjacent ordered domains. Back to the story of the example 1. The crystallized protein was expected to contain extra residues compared to the MR model. MR solution was easy, and initial refinement results appeared to be in agreement with the incomplete model. And let's look at maps. So yes, there is a density. Is it for the missing part of the model? Well, a helix fit in there, right? Let's refine. Oh no, probably helix doesn't belong to here. Refinement doesn't work. Okay, let's investigate. And when we process our raw images, we assume certain translational symmetry and integrate intensities around corresponding break spots. By doing so, we do reinforce that symmetry, and in effect, we average electron density within ordered domain and around them, and then averaged over all ordered domains. Let's see what this procedure will do to our crystal. Averaging of the top domain by crystallographic translations changes nothing. It has that symmetry. Including lower domain gives this, and domain. Domains can have negative, can have neighbors with opposite offsets. Therefore, averaging over all domains gives this. Gray C alpha trace is where we expect the Gauss density, which of course is weaker than the true one. And density for our helix is where it is expected. And here again in all its glory. And there is a procedure first used by Wong that for correction of the data. And because of strictly defined offset between ordered domains, rows of nearly perfect reflections alternate with rows of reflection affected by the disorder. Intensity of those reflections that are affected escape from the integration box, and as a result, the mean intensity oscillates in the direction of the offset. The oscillations can be compensated by multiplication with the periodic function of very few parameters. Back again to the unmodified data, and these are after correction, and this where a helix was located. Well, correction helps a little bit, but doesn't make our data as good as the data from a healthy crystal. For our example, ANA3 of 22 is a little bit higher than I would expect for 1.2 angstrom data. Density is good, however. The errors I can think of are because part of the intensity is not in the integration box. Well, it's partially compensated. Reflection profiles are different for well-ordered reflections and reflections affected by partial disorder. Gauss density actually comes from the NCS copy of the molecule, not from a crystallographic copy, and small conformational differences between those can make an effect at high resolution data. And for single crystal, we assume that any contribution to the intensity comes from randomly misaligned mosaic domains, diffracting strictly according to the Bragg law. This is not true for the disordered crystal. We need to account near Bragg diffraction. Right, I started my presentation from this slide. This is a real example, and in this example, both results of outer processing are correct, because here we deal with the allotwin, a crystal composed of domains belonging to different space groups. The packing ambiguity is again the reason for the crystal pathology. Both types of ordered domains are composed of the same molecular layers, which are packed similarly, but with different sequence of stacking vectors. The data were processed in both space groups, corresponding structures solved, refined, to give quite sensible electron density maps, but rather high R factors. One remark is needed here. Controversial results from data processing pipeline do not necessarily imply allotwining, but almost certainly they mean that this data, there will be problem with the data. In example 3, we have fourfold ambiguity of packing. In contrast with previous examples, the contacting layers are not related by pure translation, but by rotation 90-degree end translation. Packing ambiguity occurs because of a little offset shown by white marks in there. And the offset can be along X or Y, and positive and negative, resulting in 4 twin domains, schematically shown on the right. Note that intermolecular contacts here are very big. In particular, each pair of white and green diamonds makes only one direct contact through glutamate side chains. Because of so weak contacts, I wouldn't be surprised if the well-ordered P422 crystals turned into this partially disordered twinned crystals because of cryo conditions. And this is quite general. The partial disorder is a frequent consequence of cryocooling or soaking. So the control experiment at room temperature or without ligands would be helpful if there are signs of partial disorder. Despite fourfold packing ambiguity, the disorder in this example is still one-dimensional in the sense that there is only one direction along which translational symmetry is local, not global. Therefore, the diffraction patterns are similar to previous examples, streaky reflections. Well, tails of the reflections are a little bit heavier, but many low-resolution reflections are well-defined, and indexing work okay at 4-resolution cutoff. Subsequent steps eventually worked well after successful indexing. And 2 highlights here. Molecular replacement was conducted in P1 because space group wasn't known, and twin refinement required 800 cycles for convergence. Very slow. Example 4 is quite different. Crystal is composed of helices. 2/3 of them sit on the crystallographic 3-2 axis, and 1/3 on the 6-5 axis. Those on 6-5 are flipped. Therefore, there is a non-crystallographic symmetry, translational non-crystallographic symmetry, but there is no translational pseudosymmetry. The structure cannot be approximately represented in the 3 times smaller cell. Here again, we have packing ambiguity, ordered domains, and defects. Relative offset between ordered domains has a specific value of 1/3, and as a result, there are 2 subsets of reflections that behave differently. I would call reflections H minus K equals 3n strong reflections and the rest weak reflections. The strong reflections are almost unaffected by the partial disorder, while the intensities of the weak reflections are proportional to the mean size of ordered domains. The presence of weak reflection creates, with reduced intensity, creates an impression of true pseudo-translation. And indeed, our first molecular replacement model contained all the helices in the same orientation, and no surprise that that model, well, didn't refine. The disorder is 2-dimensional here, and the tails of weak reflections form hexagonal shapes around the strong ones. The correct molecular replacement solution was found, and initial refinement was performed using only the strong reflections, 1/3 of the data. The weak reflections were then rescaled to fcalc and combined with the weak ones for further model correction and refinement. And the last step was critical for correct sequence assignment. I like this example because it clearly demonstrates that pseudo-translation can come together with a partial disorder, which in this case can be easily overlooked and can make structure determination difficult or impossible. And yeah, that's a final example. Packing ambiguity again. The green-yellow dimer can jump up by 1/4 C to form a defect. As a result, adjacent domains are related by screw rotation with translational component 1/4 of C, and the domain further on the right, which is not shown here, has relative would have would be offset with respect to the left domain by translation of half C. This means that the intensities of reflections with odd index L are reduced. How much depends on the size of ordered domains again. In this case, the reduction is nearly 100%. Reflections with L even are well shaped, while reflections with L odd turned into diffuse patterns completely. Therefore, the structure was solved and refined using 50% complete data. Two remarks about such refinement. Each missing atom generates two peaks on the difference maps separated by half C, and therefore the correct one can only be chosen considering the distances to surrounding atoms. And the other remark here is that there is an alternative representation of such structures in this twice smaller unit cell, where the whole asymmetric unit has occupancy 1/2 and overlaps with its symmetry copy. And to resume, the streaky reflections mean partial disorder. Controversial results from outer processing gives an early warning sign. What we determine in these structures is the structure of an ordered domain, not the whole crystal, and results are usable, but our factors are rather high, and different crystals or different cooling condition could be a better way forward. And I thank Raphael, Xiaoyin, Zhepeng, Bo, Marie, and James for the data. I suspect I'm much happier with their data than they are, but nonetheless, these data are fully useful and useful. And thanks for your attention.